Welcome, fellow travelers, back to the shockingly long road of practicing electrolysis problems. They're starting to get a little creative with the things they ask here. They say, if a current plates out 15 grams of aluminum, how much magnesium could have been plated in the same time with the same amount of current? So, we're starting with this formula. And they tell us we're making 15 grams of aluminum, so we're heading for some trouble with this formula, but let's pretend we haven't noticed that yet, and we'll start this loop the way we normally would. 15 grams of aluminum, we think. Our formula wants moles of electrons, so how many moles of aluminum are we thinking? N equals M over M equals 15 grams of aluminum divided by 26.98 grams per mole is the molar mass of aluminum. We are making 15 divided by 26.98, 0.55597 moles of aluminum metal. Aluminum is a +3 ion, so when we turn it into aluminum, of course, it costs us 3 electrons per atom. Times this by 3, and that tells us we are using 1.6679 moles of electrons. If we go to our formula, though, we don't know anything about the current or the time. We know the Faraday constant, but that isn't enough to find the current or the time individually. They haven't told us enough. But here's the thing with these questions. They tell us we're going to use the same amount of time and the same amount of current on both metals. So if neither of these amounts changes, we can treat this like one big variable. Just pretend that it is a single value, and we can find that. We can do Faraday constant times 1.6679, and we get that IT, which we're treating like one thing, equals 160,952.6. The unit would be coulombs if you're interested. That's the total amount of charge that we put into the aluminum, and we don't know what combination of I and T made this, but we know that I times T made this amount. So then, if all this is true for the aluminum, we can turn around to the magnesium and say, all right, for magnesium, if it's the same current in the same time, then IT is again going to be 160,952.6 coulombs. So that is going to equal F and E for the other metal. We know what the Faraday constant is, so we can divide that by 96,500. And we get, not surprisingly, the same number of electrons. Really, I could have skipped this entire step and just said, look, if it's the same current for the same amount of time, we're going to deliver the exact same number of electrons, and I could have just copied this number over. If you're comfortable with that reasoning, that absolutely works. You can just go with that. Same current, same time means same amount of electrons. But if we're using these electrons to make magnesium, here's what magnesium's reduction looks like. It only costs 2 electrons to make a magnesium atom, so if we divide this amount of electrons by 2, we find we can make 0.83395 moles of magnesium. What mass is that? Number of moles times 24.31 is the molar mass for magnesium, and we get 20.3 grams. of magnesium deposited. So if you have the same amount of time and current, that means you're going to get the same number of electrons, because F doesn't change either. So you can just assume that this Ne is the same for both. In some books, instead of this formula, they give you two separate formulae, one that says Q, the charge, equals IT, and another that says Q, still the charge, equals FNE. And these two amounts are equal, obviously. This is where the it is funny formula comes from. But if you do it this way, I usually don't think this is worth the trouble, but it does mean you can calculate the amount of charge for one thing and then carry it over and use it for another thing. That's one minor advantage this has. But typically you can just remember, if you run the same amount of current for the same amount of time, you're going to get the same amount of electrons at the end. I hope that didn't bug you too much. Which of these ions would require the largest amount of charge to plate out 200 grams of metal? Okay, so we're making 4 different metals. We can kind of assembly line this. We're going to do 200 grams of sodium, 200 grams of copper, 200 grams of silver, and 200 grams of calcium. For each of these, we want to end up with moles of electrons, which means we need moles of the metal first. So for sodium, molar mass is 22.99 grams per mole. For copper, it's 63.55. For silver, it's 107.87. And for calcium, it's 40.08. So lots of calculating. 200 divided by 22.99. 8.699 moles of sodium. 200 divided by 63.55 is 3.147. Moles of copper. 200 divided by 107.87 is 1.854. Moles of silver. And 200 divided by 40.08, 4.990. Moles of calcium. Okay, so that's the moles of metal, good, but we need moles of electrons. So sodium ions are +1, as it shows here, which means it would only take 1 electron to reduce this. So this step is mathematically useless, but I'll put it in just to show you what's happening. It takes 1 electron to make 1 sodium, so we're going to need 8.699 moles of electrons to make that much sodium. With copper, it takes 2 electrons to make a copper atom. 2 electrons for 1 copper, so we get 3.147 times 2 is 294 moles of electrons. Silver is 1 again. It only costs 1 electron to make a silver atom out of a silver ion, so for that we get 1.854 moles of electrons. And last one, 4.990 times, it costs 2 electrons to make a calcium atom. 2 electrons to reduce 1 calcium. So 4.99 times 2 gives 9.98 moles of electrons. Calcium is the one that requires the most electrons, and that would mean the largest amount of negative charge. Sodium would be next, copper next, and silver would be the least. Okay, so anytime they ask for the amount of charge, that's proportional to the number of electrons. Finding Ne is all you need there. All right, Okay, we have a cell with a platinum electrode and chlorine forming on it. You have to use something like platinum or else the chlorine will eat holes in it. And on the other side we have cadmium, and it delivers current for 2 hours. Calculate the mass change at each electrode. Okay, so we have to do 2 bits of work here. On the chlorine side, we're turning chlorine ions into chlorine gas. So we have 2Cl minus turning into Cl2 and some electrons. And the current is 1.93, the time is 2 hours, which is 7,200 seconds. So our number of moles of electrons would be I/T over F. I is 1.93 amps, time is 7,200 seconds divided by the Faraday constant, and we get 0.144 moles of electrons. Now, I'm just going to reorganize this a bit. This number is true for both sides of the cell. They both have the same current flowing through them. The time is the same for both. The question is, how much mass do we get on each of the reactions from this? On the chlorine side, this says for every 2 electrons that you produce, you're going to get 1 chlorine. So, on the chlorine side, we could say 0.144 moles of electrons times, we get 1 chlorine for every 2 electrons, equals 0.072 moles of chlorine. Mass of chlorine, can I fit it in here? M and M. Number of moles is 0.072. 0.072 times the molar mass of chlorine is 70.90. 35.45 for 1 chlorine atom, but there are 2 of them. So we're going to make 5.10 grams of chlorine gas. On the other side, we get the same number of electrons. They're getting added instead of taken away, but it's still the same number, and that's what we care about. So, on the other side, we're taking cadmium ions and oxidizing them, reducing them to cadmium metal. Cd2 plus 2 electrons makes Cd. So, 0.144 moles of electrons times, it's still a 1-to-2 ratio. We get 1 mole of cadmium for every 2 moles of electrons we put in. 1 cadmium for every 2 electrons. So we're still going to get the 0.072 number, but it's 0.072 moles of cadmium. Mass of cadmium equals number of moles times molar mass equals 0.072 times, I do not remember cadmium's molar mass at all. It is 112.41. 2.41 gives 8.09 grams of cadmium. They didn't ask which electrode was which, but chlorine is getting oxidized here. Oxidation has an A in it, so this would be happening at the anode. Cadmium's getting reduced. Reduction has a C in it, so this would happen at the cathode. In case you wanted